Okay, welcome to video example number 1, part 2 of interpolation of digital topography from points to rasters. And this example along the Parkfield section of the San Andreas Fault. So I have done a little bit of work in between video 1 and video 2. And so just let me show you what we're looking at here now. So in the background is lidar raster from the B4 digital elevation model. And then um, uh, it's clipped and to this area right here and recolored in the background there um, to compare just that area where the clip is to these points where we'll create some interpolated digital elevation model surfaces or digital terrain model surfaces from the topographic survey using Total Station that we did in 2004. Okay, so just to be clear, so basically that clipping area was used to clip the lidar, and then I've recolored it to this other color scheme here. Um, and so, yeah, so I could turn off that clipping mask for a second just so you can see it clearly. Yeah, so there's the lidar in different color scheme over the clipping area. And then on top of that, we have the 2004 earthquake fractures. So we're going to see how, as we do a difference between what we interpolate for the elevation and this raster that was created from lidar a year after the earthquake occurred. We'll see if there's any changes to the topography. Those changes may be due to a difference in the production of that topography, or it may be due to potentially something that happened in the earthquake to change the landscape. That's a little bit up for debate, of course, because the survey points that we have, there's quite a few in this 2004 survey, which was done just a few months before the earthquake. We have about 3,100 points here that we're going to use to interpolate across here. Okay, so that's not as dense of a point distribution that we would have had to produce this LiDAR data set. But we're going to interpolate down to kind of meter scale resolution anyway, just for direct comparison. Okay, so let me show you what we would do here. And actually, before that, I'll say one other thing that I've done. So these points that we're seeing right here, kind of lighter colored dots, I have actually, if we turn on this other one, they're colored differently. And they're colored differently by difference between the elevation in the topographic survey from our total station and the elevation of the LiDAR data. Okay, so already we know there are going to be some differences in our interpolations because there's differences in the original points. So the way I got that information was basically if you go here, you can do zonal statistics as a table. And there's always a couple of options, right? Because of different tool packages that people pay for, but either of these work the same in spatial analyst or image analyst. If you do that, you input areas where you want to find information about some raster. And so in this case, I wanted to find out what was the elevation of the LiDAR data where these survey points were measured with the total station. So I input the survey information as the feature zones, and then you make a table where you give it the ID of those survey points, and then along with that you give the value of the raster. And so I would have went to the LiDAR from 2005, and I would ask for its mean elevation, but it's at a point, so it's not really a mean, it's just the elevation. And so I'm not going to run that now, but it saves as a table, which I have open down here, so you can see what it looks like. So for instance, um, here we get, oop, I got the wrong one open. Second, zonal statistics. So then you get the object ID, um, the count of pixels that are found within that feature, and because it's a point, it's just one, and then the value of the pixels. So you can see the mean values and those object IDs ascribed back to the original survey data. So if we look at the attribute of what the survey data looks like now, you'll see that I have the FID, um, ID, which are the same. And then I've joined in the lidar elevation. Okay. And then the original elevation from the topographic survey. And then I calculated the difference. So I did a table join to bring in that lidar elevation. But of course, all table joins are temporary. And so I then added a new field and I called it lidar elevation, made sure it was a float so it could have decimals. And then I said equals that table join, and that populated this lidar elev field with the lidar elevation data. Then I removed that table join just because when you have a table join and you're working in field calculator, it adds a bunch of fields, it looks weird. So it's always my practice to do the table join, basically copy the the stuff I wanted from the table join into a new field, and then remove that table join. Okay, so then I basically differenced from the 2005 LiDAR minus the elevation data from what we surveyed to produce this. And so here we see a 5 centimeter difference, a 4 centimeter difference of positive really change in elevation. And then here we see some negatives. And so what I'm plotting here is showing where at the points where things have gone up in elevation is warm colors, and where things have gone down is cool colors. And so what I see in this pattern right now, and I'm going to turn off this LiDAR clip just so it's a little less bias of color on color. But basically, I see cool colors wherever there's kind of nearby this channel coming out here. So maybe there was some erosion. There seems to be a line of cool survey colored points. That's probably some sort of bias in maybe the way we were reading those data, because it just seems to be coming across a zone of yellow, which is like modest positive elevation. And again, these are really tiny changes of centimeters or 10 centimeters. But yeah, so there you see lower and higher elevations. Okay, so in the end, we'll come back and look at how those point differences compare with our grid differences. Okay, so I'll turn that off for now, and then we'll see just basically the background points that were used for interpolation. So to do interpolation, we basically use a tool in spatial analyst tools. You can search for this, IDW, Kriging, etc. And it'll take you to spatial analyst tools most likely. But I like to always try to understand where in the toolboxes these tools are being utilized, because like you search IDW, yeah, you're going to get the IDW tool, but you might not realize that there's all these other options for you for interpolation. and other tools that may be useful in relation to what you're doing. So good idea to look through the toolbox as you're doing this. And let's just show you how you do that. So if I typed in IDW, and it's like, oh, it comes up in 3 different places. We're in the one in the spatial analyst tools. If I click, instead of click IDW, but I click the spatial analyst tools, it opens it up and shows you exactly where it's at, instead of just opening up the tool directly. And this is also useful because now, like if I wanted to do this on multiple files, I could right click and batch process it if I wanted. And so it's kind of, I think, a good practice to go to where the tool's located and then open it. Just one extra click. Okay, so I'm not going to sit here and make you watch all of these processes, but let me just show you what I did in each case so you can try it out yourself. So I did create this clipping raster, which you can use as a mask as you're doing your interpolation so that you only interpolate over that area. So in my interpolations, I have a few different things that were done. So we have, I'll just go to the clip ones because that was actually a secondary thing. So let me just minimize these. But maybe that's a good way to look at it. So so one of the first things I did was to create a tin. Let me turn off my mask now for just a second. So the tin is it's a triangulated irregular network based upon those 2004 survey points. Okay, and that's great, but a tin is not a raster. And so then I did a DEM from that tin. So remember, these other interpolations are all here. So that includes IDW, Spline, Natural Neighbors, and Kriging. IDW, Spline, Natural Neighbors, and Kriging, all right here under Spatial Analyst Tools. But TIN, if we go to that, we'll usually find under 3D Analyst Tools. And the tool that you'll start with is Create TIN. So let me just show you where that is. So that's under TIN dataset, create TIN. You go in here, you give it a name, you specify the coordinate system, and this is really important. Of course, you need to know what that coordinate system is for the points that you're inputting. In this case, I know that I had already pre-processed it into NAD83 UTM zone 10 for this part of California. So I could just click that. And then you input the features, which is the topo survey, but you have to specify the height field for all of these kinds of interpolations. And since I had already done added some other elevation data to it, this is important to consider carefully. You don't want to interpolate on the lidar elevations. You want to interpret on the original elevations from the survey, and that was L in this case, EL. A lot of students will just start by picking the first thing. That's not going to work. Sometimes it's ID, sometimes it's these shape whatevers. You're going to get nonsensical result. You need to tell it what you're interpolating for a height field. And usually it's elevation, but it's often something else like temperature. You're interpreting temperature in that case, or you're interpolating rainfall, something like that. It doesn't have to be elevation, but in this case it is. So then you can decide, yeah, you're using your mass points. And if you have questions about like what the options are, what does constrained Delaunay mean? Specifies the triangulation technique that we'll use along the break lines of the tin. Unchecked. The tin will use Delaunay conforming triangulation, which may densify each segment of the break lines to produce multiple triangulated edges, and this is the default. Okay. Checked, constrained, which will add each segment on a single edge. Okay, so it will have fewer triangles, I think, if it's checked. And unchecked, it will be maybe a little bit more complex. Is how I read that. I think I left it unchecked, and that's how this image came up here. Okay, so I created a tin. Again, that's not a raster. So then the next thing is tin to raster, is it? Yeah. So again, under 3D Analyst, there's a conversion in tool, which is called tin to raster. And then you take your tin, okay, and then you output a raster, in which case I call DEM tin 2004. I should have called it DTM because I use DTM everywhere else. Not going to rerun it now, but I would enter that right here. And these are all saving to my geodatabase, so I'm not giving them file extensions. But if you are saving in a normal folder, you would probably want to give it a file extension like .tiff. Okay. You want to output, you have to specify output data type. In this case, there are decimals, so yeah, it has to be floating point. And then the method of interpolation, there's either linear, which calculates cells by applying linear interpolation to the tin triangles, which is the default, or you can make it more smooth by using natural neighbors. So that may look more satisfying, not necessarily a better answer, but it does look more smooth. And then sampling distance, that's basically you're sort of specifying your cell size. So I went ahead and went to cell size, and it defaults to like 1.3 meters. But since my lidar was 1 meter data, I went to 1 meter. Okay. I ran it at 1 meter, and then you can see it pop up here. So there it is at 1 meter. It stretched a little bit weirdly. Um, Let me turn off these points for a moment. Okay, so there is my result. Um, from now you can see it is pixelated, right? It's not a tin. Um, but that was based upon this. Okay, it's colored differently, however. Right, so the tin is kind of classified, and this one is stretched in some way. If I went into the properties of this, I could make it look more similar to the other thing. Sorry, symbology, not properties. Um, yeah, so say if I went min max, no. Interesting. Oh, I see. I remember. Okay. So there's some wild data on here, some highs and lows that aren't really representative. So if I like narrow in on where the actual data is, it'll look a little different. Oh, that was not what I meant to type. Right. And so, how it's stretched just depends on what the range of data you're showing is. But anyways, that's the DEM created from a tin. So the process was first create a tin from your points, triangulate a network, and then use this tin to raster tool. Okay, so that's that one. Okay, there that is. I'm going to put the next one on top of it, IDW, and I have clearly colored those each the same, as we saw here in the just a moment ago. So let me just go back to this and go back to data set. So actually they look pretty similar, right? So there's, now it's looking right. Okay. Oh, I got you. Okay, so I had already flipped that. I see. Okay, so there was the DEM 10 result. Let's back to data set for this one. And then there's the inverse distance weighted result. So let me show you how you get that. So we go back and remember we were working under interpolation, and there's IDW. IDW, inverse distance weighting, basically looks at all the input points that are there, okay, and you can see it weights the elevations based upon points that are there, but it also considers other points nearby. And then the consideration of those nearby points are weighted based upon how far away from the pixel that you're interpolating. So if I'm asking what's the elevation of this pixel, it's going to be weighted more by this data point than that one. But it is going to consider that one, because if we go to IDW, we see we input the point fields. Okay. Again, you have to tell it what the Z value is, elevation. You have to tell it what the output cell size is. It'll default to whatever it thinks is optimal, which was near 1, which was kind of nice. I went to exactly 1. And you give it an output raster name. In this case, I called it IDW Digital Train Model 2004. And you can see what's the weighting power, and you can change that. In this case, I specified a variable search radius because you can see I have a variable point density of survey points. Some places I have a lot of points, some places I have very few. And then how many points are going to use. So basically it says we're going to change this moving window of points we want to find the 12 nearest points, and then we're going to run this analysis for each of those pixels. And then figure out an elevation based upon those inverse distance weighting. You can do other things like these barrier polyline features. I did not do that. Okay, and so this is the IDW result. Okay. And then we went to, and so if we wanted to dwell on that IDW very much, you could see that, you kind of are, it was really focused on the data that is there in a way, even though it is considering other data nearby. You can see the values that you get out of that are pretty strongly tied to the original points. So if we compare that to the tin, there's some similarities. The results seem to be a little different, but the scaling of these stretches are probably not quite perfect. So let's not dwell on that. I'm going to turn this off now and show you the next one I ran, which was the spline. I will go back to the symbology for the spline and make it more like what we've been looking at. So here's the result from the spline. Okay, so what I see there is now all of a sudden the highs and lows don't seem to sit on the points. And that's because while the values do have to go through the points in the case of the spline, they intersect, but they can bend around. So values can be higher in between points than any of the neighboring points, and they can also be lower. And so I think we're seeing that here, especially along this ridge right here that was kind of in the topographic data that we collected. One side is high, the other side is low. And so that's kind of an artifact of having this ridge. With a spline, you kind of, it's going up higher over here, so it had to go up and it has to bend back down and come up again. And then here it went down. And so we didn't see that in the other result. So the spline gives you some different weird globular uh, artifacts. So for instance, yeah, there. And then let's compare that now with the IDW. The spline is much more blobular. We can see why they might be there because we see these little highs and lows and along this channel edge here coming out of the sag pond. But I don't really like the outcome of the spline in a lot of those areas. Now it looks a lot better. We have more dense and consistent topography up on this river terrace up here. Okay, so that was spline. So to do spline, it's the same thing. You go in here, go to spline, you tell it what your points are, what your elevation is, give it an output, size, and then you have choices about how the spline is done. Regularized yields a smooth surface. First derivatives. Tension tunes the stiffness of the interpolant according to the character of the modeled phenomena. Okay, so you can try out those. And then again, it's like there's a weighting to it and number of points to consider in the analysis for each pixel. Okay, so that was spline. The next one we did was natural neighbors. And so in that one, you're going to see it creates a pretty smooth result. Again, input features to tell it what you're interpolating, elevation, output. There's a lot less choices in here. Oh, and then I should say in each of these you can specify a snap raster or the extent that you want to go to. So you can use it in a clipping mask. Okay. All right. So ran the spline and let's see what it looks like. And we're gonna turn that on. Sorry, ran the natural neighbors. We already looked at spline. So here's natural neighbors. I'll switch it back over to that other symbology. So this natural neighbors result looks much smoother to me. We can see those high points around here, but everything's just very smooth. Okay. So in some ways, that's kind of a satisfying representation of the landscape, especially since most hill slope processes kind of are diffusive and they smoothly erode as rain splashes on the landscape or gophers kick little things in kind of stochastic manners downhill. But that doesn't fit all landscapes, right? If you had a bedrock topography, um, the natural neighbors might make it everything look way too smooth than it really is. Or, after a phenomena had occurred, like say an erosion event along this little channel, that natural neighbors is smoothed it out way more than it probably really is. Okay, so keep that in mind for natural neighbors. And then the last one ran was the Kriging, which is a statistical prediction method, which is nice because it creates a pretty good result. It's not tied exactly to every one point, and it's quite tunable. And there's different methods, and right here it's telling me, and I didn't use this, that I should be considering the empirical Bayesian Kriging tool, which provides enhanced functionality for performance. So you can try that. But you do it the same way, put in the survey points, tell it what the field is for elevation, output raster, and tell it how many nearby points you want to consider, output size, etc. Okay, so I'm not going to run it, but you can see what it looks like. Okay, so go back to the data set. So there's the Kriging result. So it's quite different than IDW. Looks a lot smoother again. Okay, so I'm going to turn off IDW. Let's compare it to the tin. Similar. Sorry, the scaling is a little different. Yeah, okay, let's compare it to the natural neighbors. There's natural neighbors. There's the Kriging. If anything, Kriging is a little smoother, I would say. But it also has, so Kriging is smoother in some parts of the landscape, but it also seems to have more detail along the channel, kind of chunkier parts of the landscape. So Kriging seems to perform better than natural neighbors to me for this method. Yeah. So those were done, and they were all done, as you can see, over the area of the original tin. Um, but then I clipped everything by that polygon. So I did a batch raster clip raster. So I went to clip raster, and then I right clicked and I batched it. So let's go here, right click batch, and basically I uh, input all of those interpolations, and I clip them by this, which I drew that myself. So I say next here. Um, you can choose the output extent if you already had a clipping thing, or you can draw your own polygon right here on the fly, and that's what I did. I just put that inside a little bit of the tin just to make it a little smoother and get away from the edges of the model. Model edges, usually, you only get data on one side. It's not as good. So I didn't want to consider that too much in as we started to analyze these things. Okay, so that's the clipping area I used. Here is the results. And these are all scaled similarly. You can see I've got them between 416 and 444. So now they're kind of in reverse order. So here, this was Kriging, that smooth model. Turn on natural neighbors. Go back and forth a little bit. Turn on spline. Spline. Polynomial. Parabola is going through the data. Don't like it so much. And then IDW. Not bad. A little bumpier than some of those other ones. And then tin to raster. Oh, and that's interesting. Symbology is a little off there. Why is that? You can import this symbology from another one, and actually that's what I did for these. So I'm just going to redo that for a second. So input layers. Oh, clip DEM. I think that's what's showing. I'm going to give it the symbology of the spline. Okay, yeah, there we go. So there's the DM produced from the tin as compared to the natural neighbors. So similar result. So in terms of the ones I like the most, just thinking about how it's representing the landscape, tin to raster seems to be looking good. It's a little bit, looks like it might be 1 meter pixel bigger, and that was a little bit of a mistake if I did that, but it looks good. This one looks pretty smooth. This is the natural neighbors. I didn't prefer the natural neighbors as much as the Kriging. Okay. If you like the Kriging, and the tinned raster were my favorites. Okay, so those were that. And then just put on top of all of this now the lidar, so you can. So then there's the lidar for this same area. So just for comparison, I'll flash back and forth between the lidar and the tin clip. And they definitely are representing the landscape different. You can see the edge of this river terrace is wavy because of maybe where we collected our points as compared to the LiDAR data, so on and so forth. Okay, and so then to do a direct comparison of the topography between the LiDAR and all of these, I basically went to geoprocessing, and in here, I use what's called Raster calculator, which you can find under spatial analyst tools under map algebra. And in there, you can basically do basic operations, algebraic operations, uh, conditional operations to manipulate and calculate these data sets. So what I did was create differences, and that's what these colorful things are up here that we'll look at in a second, for each of the clipped areas. So in each case, I took the 2005 data and I subtracted it, double click, from one of the other clipped areas that was collected in 2004. So it was 2005 minus 2004. So if 2005 is higher than 2004, that means the landscape went up. And if it's negative, that means it went down. So I did that and I spit out results, and that's what we'll look at next. And so I just did that one at a time. Unfortunately, you cannot batch process through Raster calculator. You could probably set up a model builder tool and then be able to do that, but you can't directly do it in Raster calculator. Okay, so let's go back to symbology. Okay, so let's see what these look like. So subtracting uh, lidar from nearest neighbor. Um, it kind of looks like patterns that you'd see in the lidar, in my opinion. So turn that off and on, and you see a lot of kind of agricultural tilling patterns in the topography of the lidar. And you can see that in that difference map, although you see big differences over here. But it looks like a bunch of noise, kind of speckled throughout, except near the channels and stuff here. Okay. So generally near, a little bit negative, a little bit positive, depending where you're looking, except for the channels, which seem to be generally more negative. Okay, so maybe there's been erosion during the year, rainstorms. That might be an interpretation, but not a lot of signal there. Okay, so differencing between the LiDAR and the tin-based DEM is here, and this looks interesting. So here I see, again, the channels look negative, but I also see a lot of positive along the fault scarps, right, where I see where this earthquake occurred. Um, and then generally positive up here on the river terrace that's got agricultural stuff. You can still see some patterns of maybe agricultural rows and things in here. But yeah, this looks more real to me. And also in the sag pond, uh, you can see after the earthquake, it looks like the sag itself might have gotten a little deeper. Like one side went up, one side went down, and then the deep part of the sag, it got lower. Okay, so that, and then tin, that was a difference with the tin, DEM from tin. And so that was one of my preferred. Let's show you the IDW difference. And so this is a little smoother. And here, we see some phenomena that's occurring next to kind of errant high value points. So the model of the IDW, the way we had weighted it, didn't have it had enough kind of traction on the real points that those real points that had kind of errant values still have errant values, and they're showing me big differences here. But the pattern otherwise is a little similar to the previous one, the tin diff, right? In that the sag pond looks like it went down, and the fault scarp looks like it grew. Okay, so there's a similar story. And then spline I didn't really like, but let's see what it looks like. Yeah, so here we have huge positive values and big negative values here and there. Still do see a similar pattern along the fault scarp itself and in the sag pond. Um, so the real kind of signal might be there, um, but it's also confusing with these new signals that have been created because of these big bows up and down from the spline parabolas that went through the data. And then Kriging, which I liked a lot. So here's the Kriging result, and this looks pretty good. It looks similar to the tin. We see a lot of signal of down dropping in the sag. Now this signal is not very high. It's less than 20 centimeters of down dropping. It's probably just on the order of a couple centimeters in reality. But then, maybe tens of centimeters of uplift on the fault scarp at most. I don't know if these signals are completely realistic in terms of their magnitude, but I think their location and their direction is realistic. Uh, there was a magnitude 6 earthquake, which we know slipped laterally tens of centimeters. Wouldn't necessarily expect tens of centimeters of vertical motion at the surface since it's a strike slip fault, but we would expect some signal to be manifest in the landscape. And we would expect that on the fault scarp uplifting side might go up. Also in the fault zone itself, the the fault zone kind of dilates in the earthquake. So everything's kind of pushed together and then kind of creates almost like a little positive relief mole track. And so we might expect it to go up in that time. But then in areas like tension, in a kind of releasing step over like sag pond, we'd expect it to go down. And so we do see a signal down there. And it almost seems like we have some other signals going on one side of the channel versus the other. Coming off the sag pond here, erosion and uplift. I don't believe that. I think that is more of an aspect phenomenon, which could be due to the fact that the lidar was actually not a digital train model. It has trees in it. It's a digital surface model. And the lidar probably was hitting a bunch of like ground vegetation that it, basically inflated on one side and didn't have on the other. And so we're seeing some of that in the signal. Okay, so those, yeah. So doing the differencing shows us a little bit of how each model performs relative to each other. Um, in these interpolations, we can see that some artifacts or maybe bad points in the original point data that I had, like along this ridge here, are kind of coming through in that interpolated result. And so it gives a good sense for how it all works. Now we can overlay on top of this, these are all kind of scaled similarly, the original difference between the survey points and where they fell in the lidar and their elevations. And that's what's here. And we can see how the interpolations match up. So here we're looking at the point differences um, over the top of the Kriging differences. And we see a similar pattern, right? So the point differences showed that in the sag it went down. Um, and that's generally seen in the Kriging as well. We see some areas on this side, which is a mixed signal. We see some areas that kind of don't perfectly match up, but generally it's pretty good. Okay, so let's look at another one. With the spline, we should get some wilder things, right? Well, the wild things, what you see happens in the spline, the wild things happen where there are no points. So we have really positive here and really negative over here, and that's because there's no points there. So there's no constraint on the data. The IDW is here. Shouldn't be too wild since it's very much weighted by the points themselves. And then there's over the tin. And in this case, there are some minor contradictions. I can see this point here and some other little ones around. But generally speaking, these interpolations have pretty well honored the input data. They all have slight variations from each other in how they're representing the landscape. The lidar itself, this is a good lesson, right? All of these things are models about the landscape. It's not full reality, but the lidar has more like 3 plus maybe 10 points per square meter. And then we're looking at a 1 meter or half-meter pixel lidar here. And so the interpolation is having points within each pixel of the data on average. Not fully on average, not fully everywhere, because the point density of the lidar, of course, varies as you move across the landscape. But most places, you have more than 1 point in each pixel. And so the interpolation of that lidar is going to be really good. Here, our interpolations did not definitely have a point every pixel. And so the results aren't as good. But they're not bad, right? They're not bad. So if we look at comparison again with this other data. Okay, so that was it. That's the kind of comparisons between these different interpolations. We basically went through, we brought in point data, we interpolated in 5 different methods. We clipped those to the same kind of restrained area inside of the data. We then symbolized them similarly, and then we subtracted those interpolations from the lidar data and then compared the differences to help see how the differences might be manifest by the different models of interpolation. So I hope this helps as you try to think about what types of interpolation you might want to use to take point data and make continuous data across the landscape, whether it's for topography or for rainfall or temperature data, etc. Okay, thank you.